Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. For this video, I'm continuing to look through question 20 of exercise 5G of the Cambridge Extension 2 textbook. So this is the third of three questions that a student has asked for help on. I recently put out a video where I worked through 20 Part A. So now I'm going to take a look at 20 Part B. I would highly recommend taking a look at 20 Part A before working through this, because in that video I kind of went through the detail of how you would go about tackling these kinds of questions. So this question asks us to sketch a curve that's been defined parametrically by a vector equation. In 20 Part B, our vector equation has three dimensions. So we've got r vector t is equal to 3 cos t of I vector plus 3 sin t of j vector plus t of k vector. And so effectively we've got x, y and z axes that we have to deal with. For working through Part A, you'll see that basically the technique that you have to use involves picking values of t, our parameter, and for each of those values that you pick, you work out your x and your y, and then you plot it up. So in this case, we'd have to work out x, y, and z to plot it up. And the real difficulty with that is it can be quite hard to actually, on a flat piece of paper, give a good representation of the three dimensions. I mean, we can try, but it can be quite a tricky thing to kind of do it justice visually. So what I'm going to do is actually, rather than try and do that and just do some kind of feeble attempt at reflecting this curve, I'll actually use some software, because I think then we can get a much better feel for what we're dealing with. So as I mentioned, it's probably worth looking at my video for Part A so that you can get comfortable with the manual technique that you would have to use. And it would be the same here, just for three dimensions. It's just that rather than go through all of that grunt work, I'm just going to get some software to do it for me. Alright, so I've come on to GeoGebra, which turned out to be easy enough to represent a parametric vector equation in a format that kind of made it visually quite, I guess, workable. Basically, I had to just use this function called curve, and it asked for the three different, basically, I guess, x, y, z inputs. And then you had to tell GeoGebra the parameter, in this case t, and just because I could, I picked really wide boundaries for t. So if I was doing this manually, I'd probably stop at something like pi or negative pi and pi. But just because it's no extra effort, I went for some really wide boundaries. And this is the result. So here we've got our three axes. So GeoGebra's kind of picked different colors. Our kind of x-axis is this green one here. Our y-axis is the red one, and then our z-axis is this blue one coming up and down. And we can see that when we go through the hard work, in this case the computer did it, but when you plot up your three different points for all your values of t, you kind of get this spiral, which I probably would not have done a very good job of representing on a 2D piece of paper. Now the good thing about a program like this, which I didn't have to pay anything for, so it's quite a nice thing to be able to access just for free on the internet, is you can then move around. So we can kind of spin the curve around and play around with the different dimensions to really get a good feel for what we're dealing with. So for example, if I just almost focused on the x and y axis, so kind of made this flat and kind of looked at it in our normal 2D way, we kind of see that we're effectively looping around a circle, which kind of hopefully makes intuitive sense, because the x and y's are being driven by taking the cosine and sine of a parameter and kind of going back to the roots of sine and cosine. They kind of reflect effectively moving around initially a unit circle in our 4 quadrants, but here, because we're multiplying by 3, our circle just is bounded around 3. So it's got a radius of 3 instead of just a radius of 1. But basically what we're doing is, through the sine and cos functions, we're looping around that circle, and then our third dimension of z being equal to t essentially just says, and stretch it up into that third dimension, which is kind of how we get this spiral, because we're effectively looping around a circle that's then being stretched to kind of make it look like a slinky. I don't know if you've ever seen those slinky toys, but it's basically kind of like stretching out a slinky. If you took a slinky and kind of pushed it and squeezed it all together, and you look at it from above, you get a circle. And but if you're kind of looking at it from any other angle, you kind of see this stretched spiral. And another interesting way to look at this is to kind of flatten out the x and y and just look at the kind of vertical z-axis, and we basically see this familiar, essentially it's the sine curve and the cos curve. I mean, they're both the same curve, just offset a little bit. And in theory, you know, it keeps going forever. I've got quite large bounds, but GeoGebra just decided to only show this much of it. But yeah, hopefully seeing the software presented in this way kind of helps understand kind of what you're dealing with here. I mean, you could mechanically go through the steps to do all the calculations and try and draw it on a flat piece of paper, but I just think being able to move around like this really helps truly appreciate what's going on. And the reality is, I don't think you'd ever be asked to sketch a curve like this in an exam where all you've got is your calculator and a pen and a piece of paper. It's just quite a troublesome thing to try and grapple with. Again, maybe you'd be given a curve and asked to pick a function that might be able to reflect it, possibly. But that kind of 3D space, I think, really just lends itself to software like this graphing software. So hopefully, for the student who sent this through, hopefully seeing this has helped you understand what we're dealing with. I hope it's okay that I haven't gone about manually graphing it. Hopefully you can appreciate that it's probably not the most value-adding exercise to just watch me fumble around trying to do that. I think getting out GeoGebra and just seeing what it looks like, I think it's a much more valuable exercise to really kind of understand what you're dealing with. So yeah, hopefully this has kind of made sense and been helpful for you. As always, if you did find my explanation helpful, please be sure to give the video a like. And if you're someone who wants to keep your finger on the pulse with the kinds of questions that other students are struggling with, be sure to subscribe to my channel so that you can stay in the loop. Alright, tick boom.